We've
host to keep
well,
this off?
ever so slightly lost Jeff, but
There he is.
oh, sorry, he's there. Yes, sorry, there he is.
Jeff, you gotta stand up.
Sorry, Jeff, should I just start, or did you want to say anything?
No, I'll say something. Yeah. No, Stephanie said Kevin's waiting.
Oh, I see. Sorry, whistle.
Okay, well, I'm so pleased to introduce, thank you, Peter Robinson, our speaker today. Peter is professor of computer technology at the University of Cambridge, and really one of the kind of founders and kind of major contributors in what's emerging as affective computing and computational approaches to behavior. And he really kind of brings to bear both solid background in mathematics and vision to problems of understanding people and their needs and application. His research spans kind of basic science questions in terms of kind of face tracking and representation, as well as user interfaces and some of his work. His student Rana El-Kharobi, some of you may know, is a principal chief technology officer at Affectiva. I think that's one of many spin-offs that have come out of his lab, and so I'm pleased to.
Thank you, Jeff. That's very complimentary, excessively complimentary. Anyway, thank you very much for the invitation. It's lovely to be here. And I'm going to talk a bit about computers and emotions. Of course, computers and emotions aren't things that you normally associate with each other. The extrovert computer scientist is the one who looks at your feet rather than his own when he's talking to you. So why should we be interested in emotions as computer scientists? As much as how many people have a background in psychology? A few, okay, and I'm guessing the rest computer science, is that right? Mainly computer science, okay, good. So I'm going to skate over a lot of projects, best part of 10 years' work, just to give you an overview of some of the problems we've looked at and things we've discovered. But I'll go back a little in history first. Why should we be interested in emotions? Well, the answer is because people are. And the history of this goes back to another Cambridge scientist, Charles Darwin, who became interested in emotions, and back in the late 19th century, he was interested in exploring, following his work on the origin of species and the idea of evolution and natural selection, that perhaps there might be some evolutionary advantage in having a common understanding of emotional expressions. And so he worked partly with William Duchenne in Paris. Duchenne, I don't need a chair for that. Have a chair. Duchenne had been interested in expression of emotions through the face and had been capturing photographs, some of the earliest scientific use of photographs, in fact. These photographs on the right here of a tramp off the streets of Paris. What you can't see in those photographs is some of them are of him smiling after being told the joke, and in others he has electrodes attached to his face to activate the muscles to see which was cause and effect for the amusement and the movement of the muscles. And Darwin himself used various photographs of a girl here where she posed smiles and also expressed natural smiles. And Darwin took a large collection of the photographs that Duchenne had taken and tried to see if there was a common understanding of their meaning, which he did by crowdsourcing. 19th century crowdsourcing was much more civilized than using the internet. What he did was invite people round for dinner at his country house, and over drinks before dinner would pass these photographs round. These are full-plate photographs about so big. We actually still have them in the University Library in Cambridge, so if you're ever visiting you can have a look. And he jotted down what people perceived in these photographs. So here are some of the pictures that he would pass round, and he entered the results in spreadsheets. These are some of Darwin's spreadsheets, which are also in the university library, which have the names of the guests, Lord so-and-so, Lady so-and-so, numbers of the photographs, and what they perceived in them. And Darwin, in this somewhat unscientific way, decided there was a universal understanding. We actually repeated his experiment a couple of years ago and took the Duchenne photographs and actually put them on the web and had a web-based survey. We got some 20,000 participants, labeled the photographs for us, and in fact the labels under the photographs, the top row are Darwin's labels and the second row are the consensus view that came out from our crowdsourced study in 2012, and actually they're surprisingly consistent. So 130 years apart, people are still perceiving much the same thing in these photographs. So there is a common language. Neither of these are particularly scientific approaches to the problem, but makes us think that if there's a common language here, we might try and understand it. And of course, we know there's a common language of expression of emotions through the face. The whole of the acting industry, or the pictures here show a Hollywood starlet of early in the 20th century, a woman called Florence Lawrence, who was known as the Biograph Girl. In 1909, she was making 3 feature films a week, a level of productivity that you don't see in Hollywood nowadays. Now, of course, it was easier in her days. The films were only 20 minutes long, because that was as long as you could fit on a reel of film, and she didn't have to learn her lines because they were silent films. But the fact that they were silent meant that the expression on her face was her main selling point, and these photographs on her advertising card show the huge variety of expressions that she could portray, and they got labels under them which you can't read, although I will just mention that the one top left is piety and the one bottom right is sadness, and I think they're indistinguishable. So I think even in 1909 a Hollywood actress couldn't distinguish piety from sadness. In fact, there's something more subtle there, and some of these perhaps involve more than you can actually see in a still picture. They involve dynamics, and she would have been able to reveal those in the movies. But the face is an important channel for communication. We use it all the time. I look at your faces while I'm talking to you to see if you're understanding or confused or interested or bored. I'm forming a model in my mind of what you're thinking, and if you're lucky, I'm modifying what I do as a result. So we communicate different ways through our faces. Darwin was interested in what we'd now call basic emotions, half a dozen emotions that are probably important for survival: fear, anger, disgust, but also, and perhaps more importantly for computer interaction, they can convey cognitive mental states, things like understanding confusion. And being able to understand both of those classes of mental state is important. It's a way that we empathize with each other, and it's something that if you can't do, you're at a social disadvantage. It's people with autism spectrum conditions, and in that sense, computers that ignore them are autistic, and it seems that's actually worth addressing. So how can we set about labeling these emotions? Well, I have a colleague in Cambridge, Simon Baron Cohen, who runs the Autism Research Centre there, who's interested in the pathology of people who can't understand these emotions. And he devised a classification by essentially seeing what words do we use to describe these different mental states. The idea being, if they're different, we probably have different words for them. And so he just took the words out of the Microsoft thesaurus, some 1,200 words or so that describe emotions, and worked out that there were about 400 distinct, very finely divided mental states here, and the others were just synonyms for them. But in fact, you could then group these into a couple of dozen higher level classes, and the 6 of those classes are the basic emotions, essentially the ones that Darwin studied and was then studied in the 1960s and 70s by Paul Ekman, who revisited Darwin's work and undertook it rather more scientifically, perhaps. Things like fear, anger, and disgust. They're the things that you can recognize easily, and certainly you can probably recognize them from a still photograph. But the other 18 high-level groups are the ones that are probably more useful. They're more common, but they're less extreme. They're these cognitive mental states reflecting what you're thinking. And so in trying to study these, we need to have examples of them. And again, this is where the Autism Research Centre had done a lot of work. They had been interested in ways that you might teach children with mild autism, Asperger's syndrome, for example, who are very intelligent, but who have a problem recognizing these emotions. They might be able to, and they'd like to do something about it, and they're intelligent enough to learn. So Simon compiled a DVD with 2,500 video clips on it, 6 examples of each of these 400 finely graduated mental states. And build some games around it that children could play, and they could then learn a bit about emotions. And these were high-quality videos. They'd been carefully validated by a panel of expert psychologists, 8 of the 10 of whom had to agree that they were a good representation of the emotion for it to get on the DVD. Well, this, in the machine learning world, is training data to kill for. So this is excellent. And Simon ran some trials with this DVD and discovered that children were extremely good at recognizing any of the 2,500 video clips on the DVD, but they couldn't generalize particularly well from it to other video cases. Well, that's what we thought we might set about doing. But the first thing we wanted to investigate was, is time important? Can you work with still pictures, or do we actually need to analyze video clips? And to do this, we took these video clips. They're between 5 and 10 seconds long. We cut each of them up into 5 segments and then ran a trial where we showed people initially just the final segment of the 5, and then the last 2/5, the last 3/5, 4/5, and then the whole video, and observed how their ability to recognize the emotion varied with the length of the video clip they were shown. And we got 2 quite different classes of result out of this. The blue circles along the top, this is on a forced 4-way test. We're seeing about a 3/4, 75% recognition rate, pretty well constantly for the basic emotions, the 6 Ekman basic emotions. But for the complex, the cognitive mental states, we're seeing that the recognition rates increase from about 50% up to 70-75% as we increase the length of time that people see it, up to about 2 seconds. And then beyond that, you don't get much improvement. So there is something in the dynamics that would seem to be important, and that can inform the design of a computer system, for example. So when I say we, I mean my student, Rana El-Kalioubi, put together a system where you just point a webcam at someone's face, track feature points on it, and then from those make inferences about action units, from the action units inferences about gestures being sequences of action units. So if you've got head up and head down action units, a sequence of head up, head down is a nodding gesture, and then combinations of the presence and absence of gestures, together with a bit of history, can tell us something about the mental state. So this is sort of the architecture of the system. It's a layered system. We were using a commercial feature point tracker. This was 12 years ago now, so some while back. And from that we could make inferences about head pose and, as I say, work through this system using machine learning techniques for the recognition of the gestures, so sequences of action units, and machine learning for the mental states that we inferred at the end, which also used a certain amount of history. And here you can see the system operating. This is a young lady who was being asked to act as if she was agreeing. What you see is the video clip. You might see certain spots on her face. We didn't paint dots on her face, that's just diagnostic information. On the left, there are various gestures being recognized. The one at the top is nodding, which you'll see was quite strong. And then across the bottom, we have the inferences for the different mental states. And red is agreeing, and you'll see, well, after a couple of seconds, and it takes a couple of seconds to kick into action, we see the red trace of agreeing. And then, in fact, she stopped to see if it had worked. And we saw little bursts of green, which is her being interested in what's happened. Yellow, she was a bit unsure. Was she meant to have acted a bit more? Blue, concentrating, and then a bit more nodding. So if I show you the video again, you'll see that as she nods, we get the agreement kicking in. There's a little pause where we got a dip, and then she stopped, wondered whether she should be doing a bit more, realized she should, did a bit more nodding, and so on. So that gives you the sort of general picture. We used the videos on Simon Baron-Cohen's DVD to train the system, both at the gestural level and at the mental state level, and then using Leave One Out to test it. And there are difficulties with this. So this is one of the videos off the DVD, and if I were feeling we had a bit of time to spare, I'd ask you which of these categories you'd put it in. Is she agreeing, concentrating, disagreeing, interested, thinking, or unsure? Well, in fact, let's do that. Let me just show you that again, and then we'll take a quick popular vote. So, who thinks that she was agreeing? No, one or two maybe. Concentrating? This is one or two, yes. This is terrifically unscientific. I do hope you appreciate that. Disagreeing? Okay, interesting. Half a dozen. She's showing interest? No. That she's thinking? Oh yes, quite a lot, about 2/3 of you. And that she's unsure, not that you're unsure. Just under 2/3, I'd say. And that's pretty typical of what we see. So firstly, these facial expressions are ambiguous. It's not as if some of you are wrong, it's just that we interpret them differently. And if we actually look at what the analysis from the system is for that, it turns out that that was the fine-grained category of brooding, which falls within the thinking group. But if we look at the analysis over time coming out of the system, we see that there's a purple line of disagreeing, which quite a few of you perceived, that the system would also have perceived early on in the video. And there's a little bursts of agreement at the end, perhaps, and concentrating. But the two ones that dominate for any length of time are the brown trace, which was unsure, and the yellow trace, which was thinking. So if one had to choose one of them, you'd probably say the one with the largest area under the curve, that's yellow, thinking, which happens to be the label that was on the original video. But you see there is ambiguity here, and that's something that's makes computer scientists uncomfortable, but it's important to be able to deal with it. In fact, if we look at the confusion matrix of the testing of this data, we have the ground truth labels running across the bottom here, the inferences running into the distance, and the good news is you see a very strong diagonal, so by and large it's making the same inference as the label. It's particularly strong for the green column concentration, which is about 90% of the time it's getting right, and particularly low for the blue column thinking, which is only getting right about 65% of the time. But there again, the confusions are not unreasonable. Thinking is being seen as concentrating or interested or unsure, all of which are sort of fairly reasonable alternative interpretations. So what that tells us is, yes, this can work, but we've got to remember that this data is it's not like attaching a voltmeter to the person and understanding what their feelings are. It's a hint, it's ambiguous, and of course there may be several expressions simultaneously, which we're not discussing yet. Well, never mind, that's good enough to be interesting, and As Jeff mentioned, Rana's taken this to market in the system from Affectiva, or Aftex, I've forgotten which it's called this week, where they're using a tool rather like this to measure just some characteristics of people, typically audiences watching things like commercials or political debates, and to measure their happiness at what they're seeing. And it turns out that this is quite a viable commercial system. It's all been rewritten, I might add, since the early days in the lab. But of course, there are other ways you can try and represent emotions. This set of discrete labels is, in some sense, difficult to work with, and another way would be to take those emotion words and see which ones have similar meanings and which ones have different meanings and which ones have opposite meanings. And this was the analysis that Jim Russell did back in the 1980s, and arranged the words, essentially did a principal component analysis on the associations between different emotion words. And the two principal axes that you see here are the horizontal one is what's called valence, sort of the going from something that's negative on the left, miserable, frustrated, over to something positive on the right, satisfied, pleased. And the second most significant axis is activation, so from passive at the bottom, tired, sleepy, up to active at the top, aroused, excited. And you can have combinations of these, and there are, as you work through the axes, these two cover slightly over half of the variance in the positioning of the words, but you can pick up other axes like potency from weak to strong, tendency inward and outward, and so on. And so that seems like another interesting system to try and automate the inferences within this dimensional space. And so we have a more recent system that works on this basis, using a different form of face tracker, which identifies rather more landmark points on the face, about 68 points around the face. Having identified a face and those feature points, we then align the face into a standard frame, where using fixed points on the face, like the sides of the cheek, the bottom of the nose, things that aren't actually moving much with expression. We can use those to align the face in a precise size and orientation, so that we can then use video techniques like a histogram of oriented gradients to measure the appearance within that, and combine that with the alignment information, which is giving us some geometric information about the face, and we end up with a huge dimensional space, and then use principal component analysis to reduce it down to a set of features, about 1,400 features that cover 95% of the variance in the faces. And then, well, having got those features, you can then try and interpret them however you like. And we've tried a couple of techniques. We've been trying to recognize action units. This is from the facial action coding system that Ekman devised in the 70s, of things like head up, head down. What we find is, by adding after this sort of level of features, well, first of all, we have to do a little bit of normalization, because different people have different amplitudes at which they express these emotions. And so what we do is, as the action proceeds, we obtain the median value of the various features in this multidimensional space, and then just normalize with respect to the median, so that we can see on per person how active that is. And from those we can then infer, well, the action units, and then from action units we can either interpret them as valence and arousal just by using various bits of training data, or we can use a categorical emotion, just using essentially tables of which action units are associated with different emotions. This system for action unit detection, and also the intensity of the action units, turns out to be quite effective. So here's a video of it working. This is Tadas Baltrushaitis, who built the system, who will shortly be arriving here as a postdoc. Regrettably, you seduced him. So what you see is him acting. You see the 68 feature points on the face. This is the normalized face, which you'll notice is not moving as much as the real face. Histogram of oriented gradients. These are the various action units, so from lowering the brow to, oh dear, lost the picture. Let's do it again. So things like chin raise, cheek raise here and so on. And then there is a point that's drifting around the valence arousal space there, and also the tracers running beside it, just showing the sort of the history of recent values. And an inference of, in this case, some of the particular emotions. And this turns out to be quite a reasonable analysis. We've trained this using 3 of the standard databases of emotional videos, and the F1 figures for recognizing 3 of the emotions are sort of reasonably good. Action unit 12 is smiling. It's the one that's easiest to recognize. We're getting about a 0.83 F1 figure for that, which is reasonably good. And we can also then do support vector regression to try and evaluate the strength of the emotions, and for that we're seeing Pearson R² figures that are reasonably high again. So this is a plausible system, and we've been using this ourselves in a European project that's been investigating the way in which we can help children with high-functioning autism to learn about emotions. And the idea is they have essentially a game that they play. It's an adventure game where they're solving puzzles. The puzzles tend to involve things like recognizing emotions, recognizing emotional situations, and also acting emotions. And their performance in acting the emotions is evaluated automatically using this system for facial expressions, a system from our colleagues at the Technical University of Munich analyzing vocal expression, and a system from our colleagues in the University of Genoa that interprets body posture and gesture. And that gives feedback to the children and allows them to understand whether they're acting these emotions properly or not. And initial trials, it hasn't been clinically tested yet, but the initial trials suggest that at least the children enjoy playing it. We'll know later whether it actually has any quantitative effect. But as part of this, we had to prepare new test data, data for the games on the that will be played, the emotional videos, and there were 20 discrete emotions that were being used, and about 500 videos were collected of these, and then these were validated using a crowdsourced technique, actually. So 50,000 assessments collected online of these 500 videos, so an average of 100 assessments per video, which was a 6-way forced choice between the correct label, 4 foils, and none of the above. And of the videos we'd recorded, 3/4 or so actually got the correct label more than half the time, and so they're ones that we can consider. And the people doing this were also invited to say on a 5-point Likert scale what sort of valence, arousal, and intensity they perceived in the videos. And this was actually one of the more revealing parts of the study. If we look at the 6 Ekman basic emotions, what you actually see here are the prediction intervals, confidence intervals for the 2-dimensional distributions. If we treat the valence and arousal samples from individual people as samples in a 2-dimensional normal, and we can see that things like happy is seen as having positive valence and positive arousal, surprise, less positive, but rather more dispersed. But all the negative emotions, disgust, anger, fear, and sadness, are actually more or less indistinguishable in terms of valence and arousal. And that perhaps says that valence and arousal aren't really such good measures to be using. They rather appeal to computer scientists who think, good, we have two numbers, that specifies an emotion. And what we see from this is it's nothing like that. Firstly, there's variance, and secondly, there's considerable overlap. So you've got to be very careful when you're using that sort of language. However, this does give us a tool for giving feedback to children, because we can ask them to act an emotion, and as long as the acted valence and arousal lie within the prediction interval, then it's probably a good emotion, a good representation. And one of the things that we've been looking at is providing formative feedback to children acting emotions. So if we take our main pipeline of video analysis leading through to valence and arousal, if the value that the child performing gets is some way distant in the valence arousal space from that which we'd expect, we can identify a correction vector that needs to be applied, and then there is a technique called Parson window estimation, which you can use to push that back into the feature space, the high dimensional feature space, as an explanation vector there, which of course has very little real life meaning, but tells us what we would have hoped to have seen back in the feature space. We can then subtract that from the values that were actually seen and identify the correction vector that needed to be applied in feature space, apply that forwards, and we can get formative advice in terms of action units, which is a reasonable language to use to say that you needed to raise your chin more, open your eyes more, or something of that sort. And so, again, this is being experimented with at the moment. Well, that's some of our work on facial expression analysis, but we've also looked at other modes. There are other ways that we express emotions through the non-verbal characteristics of voice, the energy, the tempo, the pitch of a voice, through body posture and gesture, and indeed we're interested in animating cartoon figures so that they can show emotional expression in conversations. So I'll say just a little bit about some of our work on these as well. Working with voice is different. Firstly, the facial expressions are this very convenient language of action units, which is a nice descriptive language for things that happen in the face. And there isn't a similar language for voice. There are all sorts of metrics you can measure. You can work out energy in different frequency bands. You can work out derivatives of that. You can work out the overall energy. And it turns out that none of these indicate an emotion as directly as some of the action units indicate an emotion in the face. But it turns out if you've got a pair of conditions, you can usually find one or two features of the voice that will allow you to separate those two conditions. So what we do is, if we want to distinguish, say, 6 different mental states, well, there are 15 pairs of mental states to be compared, and so we can use data mining techniques to identify the correct features to separate each of those 15 pairs. And we work within a space of features that's got about 200 different features in it. So these things like energy and frequency bands and the derivatives and the second derivatives and so on. And that allows you to do pairwise separations. And if you then want to classify a particular voice sample, all you do is do the pairwise comparisons with all the different pieces of reference data. And that gives you a large number of pairwise comparisons, which you can then combine using something, well, a bit like a proportional voting system. You have preferences, so it's more likely to be emotion A than B, more likely to be A than C, more likely to be C than B. And you then try and resolve these and identify a main winner. And you can get, this turns out to be a very powerful technique because you can plug in different sorts of voting system here. You can have a single winner, which is in fact the confusion diagram shown at the top left there. This is actually working on 9 different conditions. Again, you see a fairly strong diagonal and some off diagonals. The weakest diagonals probably excited, the orange bar, and excitement can easily be associated with different mental states. But by allowing multiple winners, and one simple algorithm is simply to say we'll accept any classification that exceeds, that wins more than half of its pairwise comparisons. So you get this second picture, which has a much better diagonal. Of course, it has many more values off diagonal as well. And that's probably the correct interpretation. It's not as if each sample only represents a single mental state. There will be several interpretations present, even if it was only intended to exhibit one. And so this allows us to express that there's multiple co-occurring states. And this is a useful technique, and we've also looked a little bit at ways of combining the facial expression and the voice and doing multimodal analysis, both with a late fusion, which actually we've used in some of the games for the autism project, and also early fusion, which gives some improvement in the accuracy. The difficulty there is there's a shortage of good multimodal training data. Well, there are other ways that you can express emotions. I mentioned body posture and gesture. And of course, there's ambiguity here. There's some famous pictures of tennis players exhibiting various emotions, and some of them are pleasure and some of them are displeasure. And actually, from their facial expressions alone, it's pretty well impossible to tell which is which. But if you actually look at the complete pictures, actually their hand gestures pretty well tell you that if the fist is clenched, it means one thing, and if it's open, another. And you can then perhaps see it's the open hand is perhaps the less pleased, and the clenched fist is more of a success. But all it says is body language is important too. And so it would be interesting to try and analyze people's body gestures and the dynamics of their movement. The snag is when we were doing this, it was quite difficult to track someone's body. You had to, we were using a Vikon system, so you had to dress up in this rather attractive leotard covered with retroreflective dots to act. Now, a Vikon system is a very precise piece of equipment. It can track 20 or 30 of these dots to millimeter accuracy at 200 hertz. But it's kind of an expensive thing to do, and it's not sort of thing you have around the home if you look at the monitor of domestic environment. But it allowed us to do some early experiments. Of course, now you would try something like a Connect, which gives you very nearly the same precision in recovering the skeleton, but at about 1,000 of the clock. So probably won't have Vikons in all our homes that soon, but Connects we might have. But then analysing the information you get back. So here we see some skeletal models that have been captured of actors, in fact, data gathered by some people in Glasgow, of actors undertaking 4 activities: knocking, which you see here, lifting, throwing, walking, in 4 different ways, sort of neutral, angry, happy, sad, and then multiple data of all of these. And you can perhaps see that there's the one on the left has slightly more vigor to it, and has anger, whereas the one on the right was actually lower vigor, a sadder approach. So can we distinguish those automatically? Well, it turns out if you just take the joint angles and their derivatives, which tell you something about the speed of the movement, and what you discover if you just do a simple machine learning is you discover what the action was that was being done. And that's not terribly helpful. So it turns out that what you have to do is segment the data into small components of action. So for example, for knocking, there's an initial rise of the hand, and then there's a strike, retract, strike, retract. More about how the motion is being done rather than what the motion is. Movement is very person-specific, so it turns out you have to account for the individual. You have to train the system on the individual. Some people are just naturally more dynamic than other people, and you have to factor that personal motion signature out before you can try and classify the actual emotion that was attached to the action. And the sort of results that we saw were if we segmented the data, we improved the recognition rates a small amount, but the real win was factoring out the individual bias of a particular person. And this is on a four-way forced choice. We could move the recognition rates up to 80% from below 50%. So recognizing an emotion from a body gestures, from the dynamics of the gesture, built a system that can identify various different hand gestures over the face. This is a seriously hard vision problem because the hand has the presence of the hand and these different touches in different parts of the face. medical students, trained half of them with the robot, the other half not, and expose them to a patient with dystonia, we could actually see that the ones who had worked with the robot in advance were able to control their reactions better. Of course, it's probably, if we'd just shown them a video in advance, we should have perhaps done that as a control, but it's a possibility. And we're still interested in this. We do know that the more realistic looking the android head is, the more people empathize with it. And so there is something to be done here, but we are getting close to, I suppose, what people call the uncanny valley. I'm nervous about phrases like that because I don't think it's been particularly scientifically investigated, but certainly people found this robot slightly unsettling to have a conversation with. Well, I'll just finish by saying a little bit about possible applications of this work. And one of the things that interested us is monitoring people in everyday interactions with computers. And of course, the computers they interact with a lot are embedded computer systems, things like satellite navigation systems in cars, and so on. And that's perhaps an example of a more general case of command and control operators in complex situations. Can we see cognitive load on their faces? Can we, in a non-invasive way, see that somebody is stressed? And if you're driving a car and you're in an unfamiliar city centre, the traffic's busy, you're lost, you're late for a meeting, the last thing you want is a satellite navigation system that tells you to make a U-turn. It's likely to cause an accident. And a more intelligent system would see that you're confused, you're concentrating, and it would do helpful things like stop your cell phone from ringing, turn off the radio so you weren't distracted, maybe even let you drive in the wrong direction for a bit to recover your composure and come back in. So we thought it would be interesting to try this, and we did some experiments with a driving simulator. This is our driving simulator, which we again bought a very expensive driving simulator that's used by the motor companies and then rigged it up with controls that you can buy if you're keen on playing race games at home. This is currently what you have. Put up for a projector and away you go. The trouble is that the commercial driving simulator had lousy graphics, no instrumentation, so we didn't know where on the road you'd driven. You couldn't really control the other traffic, and the map was pretty small. So then we got hold of a copy of Grand Theft Auto. Grand Theft Auto, it turns out, has good graphics. There are APIs where you can get good instrumentation down to centimetre accuracy of where the person has driven. You can control the other cars and the weather, for that matter, and it has a large route map on which you can run your own route planning. So it turns out that, again, for about 1/100th of the price of the commercial product, we got a rather better domestic product, and there's probably a moral lurking in there somewhere. So we play Grand Theft Auto. And here you see me going for a drive around San Andreas, I think. For various reasons, I have the robot sitting next to me. This is to do with it turns out if you want publicity, get a robot. You probably know that here anyway, but the press love robots. They thought I was actually suggesting you should have a robot sitting next to you in the car instead of a satellite navigation system. Well, without the robot, we still had people do various tests in this driving simulator. And it was disappointing. We were getting them to drive in different weather conditions, different traffic conditions, and also with making them do mental arithmetic while they were doing it to increase the stress levels. And we could see that we could increase the stress, and they crashed the car when we made them do too much mental arithmetic. But they didn't care. There was essentially no reaction on the faces. There was no emotional engagement. They knew it was a game. So then we changed the system slightly and got hold of some of these cheap domestic drones, these things you normally fly from a mobile phone. We reprogrammed it so it could go on the infrastructure Wi-Fi network in the lab so that you could drive it from the same position in our lab, but then you take the drone off for a trip around the lab, around an obstacle course, but we have the driver back in the lab so we can instrument them with physiological measures, monitor their face, and so on. And this allows you to do rather more scientific measurements of people, but there was real emotional engagement because they can hear this thing going down the corridor. If it crashes into the wall, somebody's got to go out and pick it up. And of course, you have the added fun, you really irritate your colleagues around the lab by flying into their offices. And so we did various experiments with this, and this shows you the sort of thing that we were able to do. And we actually found that this actually had quite an interesting effect on the physiological measures. So, complicated picture here. What you see are 4 graphs. On the left-hand side, driving simulation. On the right-hand side, remote control of a helicopter. Top measure is essentially a skin conductivity arousal measure, and the bottom one is a heart rate arousal measure. And then within each box, you've got easy conditions and hard conditions. And what you're seeing is essentially for the driving simulator, no difference between easy and hard conditions. Even though people were crashing in the hard conditions, we weren't seeing any level of emotional engagement. But with the remote control helicopters, we actually found quite significant differences between the easy and hard conditions. And it's because there is a genuine emotional engagement. It's a real thing. And so this is quite an interesting observation. If we're trying to do real-world studies, taking drivers out onto the street is a bit difficult. You can't arrange for all the other traffic to drive exactly the same way every trial, so it's hard to get reproducible results. In the lab we can, but with a driving simulator, they're not going to be meaningful because people aren't engaged. But with the remote control devices, it seems that we can actually have the person in the lab running repeatable experiments, but also get emotional engagement. Perhaps a useful lesson. Well, I probably ought to stop there to say that there are a whole family of problems that I've talked about, from different classification systems for emotions. I haven't really spoken much about data collection and labeling, but that's all of these systems use machine learning, and we need labeled data, lots of labeled data. It seems that some of that labeling can be done by crowdsourcing now, especially if you wrap it up in a game on Facebook. People will actually label data for you for free. A lot of work on machine learning and inference, a little bit of work on animation, and various work on different modes. And we're beginning to look at applications, and actually the automotive applications seem to be interesting. It's the sort of thing that car manufacturers actually beginning to want in their cars. So actually have a project with a large motor manufacturer in the UK that wants to put driver monitoring systems into their cars. Well, I ought to just finish by saying, of course, I haven't actually done any of this work. It's all done by the extremely talented graduate students and postdocs who've worked with me. These are the people who actually deserve all the credit. Meanwhile, thank you very much for your attention. Thank you. And I'd be happy to take questions if you have any. Yes.
I know that you are more with computer, but would you be interested to understand, have insight, how those autistic children react to what you produce on screen with functional MRI or electro?
Yes, I'd be...
just to see where it's clear.
Yes, so Simon Baron Cohen is very interested in that. Of course, he has theories about the genetic origins of autism, and yes, there would appear to be difference in I'm a little bit skeptical about functional MRI as an investigative tool, but set that aside, I think there is something there, and it would be interesting to look at it. One of the things that interests Simon is the genetic nature of autism, and therefore, if it's present at birth, can you detect it at birth? And he's done studies that suggest, yes, you can. Actually, one-day-old babies show different eye movement responses to different sorts of subject material on a screen or a photograph. And we were interested in seeing whether we could make a very early diagnosis system for autism out of that. Because normally you can't really diagnose till about the age of 3, and we know that early interventions are helpful. So if you could diagnose at birth, early interventions might be even more helpful. Unfortunately, of course, you don't really know which children are going to have autism, so we would have had to study every child born in Cambridge for a year. So that's about 100,000 newly born children, which was fine. Seemed like that was an interesting project to do. Unfortunately, it took a lot of funding, and we haven't yet managed to find anyone who's willing to fund it. But that would also have involved MRI scans at, early on. Yes. The only thing I can say about this intervention is that the children with Asperger's love it because they like computer games. We had some, I didn't talk about it, but some games that they could play with the robotic head as well. And they like that as well because it has robots they empathize with, they're mechanical, they're predictable, and so they like playing games with that. So it's just that we couldn't really get it to do the things we wanted well enough to conduct scientific trials. But yes, anything like that would be interesting. Sorry.
You said a few words about emotional engagement. I wonder, how do you measure that?
Emotional engagement in the trials that we were running with people, emotional involvement with the game. Well, it was just the observation that we weren't seeing any. You mean on this slide? We just weren't seeing any physiological responses. Now, I'm not physiological measures of arousal are a marginal benefit, perhaps. I mean, I'm not entirely convinced. They're in no sense an absolute measure, but as a differential measure, we should have been able to see something, and we weren't. And it was true. We could just see that in the videos, that people laughed when they crashed the cars, whereas they didn't laugh when they crashed the helicopters. And so, yes, is emotional investment the right word? I mean, they cared about the outcome of the helicopter experiment. They didn't particularly care about the driving simulator, was really all I meant by that. How do we measure it? Well, this was, let's say, skin rate and heart rate, skin conductivity and heart rate were the two physiological measures we were using there.
Just a follow-up on that, did you have any video of their faces?
Yes, I mean, we were recording the video, yes.
And did you get coherent facial expression?
No. Well, only insofar as they weren't looking. I mean, it was just pointless. They were just clearly not terribly. I mean, we were using the physiological measures essentially as the ground truth, but there was no distinction in the ground truth, so it wasn't worth pursuing the analysis of the videos. Oh, here, this, yes. We never actually got around to doing the analysis. We didn't have quite such a good facial analysis system then as we do now. We should revisit it. I think we still have the videos, yes.
Perhaps I missed it, and I could look at the papers, obviously, but in the work on the voice, could you talk a bit about what parameters of vocal communication are most useful?
Yes. Well,
I was imagining things like pitch or...
yes. So what we were actually doing was initially collecting really a lot of different measures. So 173, 200 odd features that were being measured continuously as the voice samples came in. So any number of statistical operations applied to the pitch, energy, tempo, harmonics.
It's a package then.
Yes, we were just using a standard package that gives you all these metrics, but then we'd find that to distinguish a pair of conditions, usually only a couple of these, 2 or 3 of these metrics would be sufficient to separate them.
I guess what I was trying to get at is, are there certain features of the voice that you think are particularly diagnostic or useful?
No, precisely the opposite. I think that the observation was it was different features to distinguish different pairs of conditions. So that was the lesson that we learned, that there was nothing like action units that were strongly associated with particular conditions. It was just for any pair there would be something that would be appropriate for separating them.
Yeah, have you thought about the application of those work for understanding effect of dysfunction in mental illness like depression or schizophrenia where they show deficits in emotional expression or reactivity? Like, could this be used to create a model for that, to understand that better, or to perhaps detect early subtle changes earlier on in the disorder?
Oh yes. Well, Jeff knows about this, monitoring depression, and also have a project with Ros Pickard in Boston where we're monitoring a large number of patients with depression going through some of the city hospitals. They're using physiological measurements and trying to, so they're monitoring their physiology, skin conductivity mainly, the 24 hours a day, and then investigating the correlations of that with the more conventional measurements when they come in for their appointments in the hospital. And I mean, well, about 6 months into the study now, so it's a bit early to say what sort of thing, but you know that Ross has had some success in using skin conductivity measurements to anticipate epileptic events, for example. So no reason to believe that's associated with depression, but just to say that it does seem that this sort of arousal is linked to depression. The difficulty there is that those sort of physiological measures don't seem to have strong absolute baselines, even for an individual person. So they're much better as differential measures, and quite how you accommodate that in the analysis, we're not entirely sure yet. But I don't know, Jeff might have ideas on that.
I mean, I think person-specific measures is a useful way to go, because physiological reactivity varies so much across individuals. I mean, in the case where you're trying to screen for depression, that's a very difficult problem. But in the case where you're seeing people over time, as in a clinical trial or treatment, then it's really possible to introduce classifiers that are using both general and person-specific. We did some work in a clinical sample, clinical trial, and about 50 people seen over 20 weeks, and over 60% of the variation in their depression severity was accounted for by vocal timing and switching pause latency and vocal frequency of both the patients. So I wanted to, just, if I could, just follow up on this question that John asked about the audio features of motion. It strikes me that what you found may be like action units, yes? In that you're saying that the number of features that distinguish any particular kind of emotion or mental state was relatively small. I mean, isn't that a little like...
Sorry, that wasn't quite what I said.
Okay.
It was that if you've got two mental states that you're trying to distinguish, a small number of features will separate them. So if we're trying to separate A and B, there'll be a couple of features. If we're trying to separate A and C, there'll be a couple of different features, and B and C, a couple of different features again. So it's not as if they're associated with the A, B, and C, they're associated with the pair.
I don't know, I'm thinking sort of action units correspond to muscles. If I'm trying to distinguish the brows being pulled down and together versus up.
Yes.
I want to know about frontalis and corrugator. No, there's no analogy there?
Well, not that we found, but I wouldn't be so rash as to say that there isn't. I think clearly energy relates to, it's a strong indicator of anger and things like that.
Okay. Any other questions? Okay, well, thank you. Thank you very much.
Thank you very much.
My name is